In this video, I'm going to share on buffer. I'm going to explain types of buffer, and I'm going to show you step by step on how to calculate the pH of acidic buffer solution before the additions of small amount of strong acid or strong base. Hi, I'm Teacher Tan. If you like my video, do remember to click on the subscribe button below so that you won't miss any notification as I update my channel. When a small amount of strong acid being added into water, we can see a drastic drop in pH. And if a small amount of base is being added into water, a drastic increase in the pH can also be observed. However, if we repeat the same things in the buffer system, we will only see a slightly change in pH. For example, if adding a small amount of strong acid into a buffer system with pH 4.74, we could possibly observe only a slightly drop in pH, for example, to 4.68. The same observation can be seen if we add a small amount of strong base into a buffer system. We will only observe a slightly increase in pH, for example, from pH 4.74 to 4.80. What are actually present in the buffer to allow the buffer to receive only small change in pH when strong acid or strong base is being added into the buffer system? So, what is a buffer? Buffer is a solution that can receive drastic change in pH when small amount of strong acid or strong base is added. Basically, there are two types of buffers: acidic buffer and also basic buffer. For acidic buffer, the component in the acidic buffer include weak acid and the basic salt. Between the weak acid and the basic salt, there must be a common ion. For example, in the acidic buffer, the components will be weak acid, acetic acid, and also the basic salt, sodium acetate. Between the acetic acid and also sodium acetate, the common ion is acetate ion, CH3COO-. For basic buffer, the components include weak base and the acidic salt. Between the weak base and also the acidic salt must also have the common ion. For example, in the ammonium buffer, so the weak base will be the ammonia and the acidic salt will be the ammonium salt. Between the ammonia and the ammonium salt, the common ion is ammonium ion. Now we move on to look at the acidic buffer. In acidic buffer, it consists of two components. The first one is the weak acid and the second one is the basic salt. The weak acid, acetic acid, will dissociate partially in the aqueous solution to give CH3COO- ion and H3O+ ion. While for the basic salt, this is a sodium salt. So sodium salt, remember, it is a soluble salt. So soluble salt will dissociate completely in the aqueous solution to give respective cation and the anion. Now we move on to look at how to prepare acidic buffer solution. Acidic buffer solutions can be prepared from weak acid solutions. Weak acid, again, it dissociates partially in aqueous solution. So when it dissociates partially, means that the dissociation reaction is reversible. Hence, it will form an equilibrium. Before the basic salt is being added into the weak acid is in an equilibrium system. When the basic salt solution is being added into the weak acid solutions in order to prepare the acidic buffer, the equilibrium system of the weak acid is being disturbed. It is being disturbed because when the basic salt dissociates, the anion of the salt is same with the conjugate base of the weak acid. Hence, the equilibrium system here is being disturbed by increase in the concentrations of the conjugate base CH3COO- ion. When an equilibrium system is being disturbed, according to Le Chatelier principles, the system will respond to reduce the effect of the disturbance in order to reattain an equilibrium. Now, the equilibrium system is being disturbed by the salt due to the presence of the common ion CH3COO-. So the system is being disturbed due to increase in concentrations of CH3COO- the conjugate base. So the system therefore will respond to reduce the concentrations of the conjugate base CH3COO- by shifting the equilibrium positions to the left. When the equilibrium positions is being shifted to the left, the amount of the weak acid CH3COOH will increase. Or in other words, the weak acid will only dissociate slightly due to the presence of the common ion CH3COO- from the salt. Then, we can make two assumptions for an acidic buffer solution. First, there is slightly or almost no dissociations of weak acid. Therefore, the weak acid concentration is equal to the initial concentrations of weak acid. And for the conjugate base, since there is no dissociations of weak acid, so all the conjugate base is therefore from the salt dissociation. And hence, the concentrations of the conjugate base must be determined from the concentrations of the salt. To calculate the pH of acidic buffer, we can use the Henderson-Hasselbalch equation, where pH of acidic buffer is equal to pKa plus log concentrations of conjugate base to the concentrations of weak acid. In order to calculate the pH of an acidic buffer before additions of small amount of strong acid or base, first we must be able to identify how was the buffer being prepared. So whether it is the ready-made, where the basic salt and also the weak acid solutions are already been mixed. Or in the case number 2, at first we have weak acid and also basic salt solutions separately, and then only mix the solutions together in order to prepare the buffer solution. Or in the case number 3, we have the weak acid solution and the basic salt are being added into the weak acid solution in the powder form. Different ways of preparing acidic buffer solution will have slightly different ways to calculate the pH. Calculate the pH of acidic buffer solution before additions of small amount of strong acid or base. Step number 1, we need to identify the case. Like for this question, we have been given the molarity of weak acid 0.12 molar lactic acid and also the molarity of basic salt 0.1 molar sodium lactate. So if the molarity for both weak acid and the basic salt are being given, that means that this is case number 1, ready-made buffer solution. After identify the case, then in step number 2, we can list down the molarity or concentrations of weak acid. So must remember, for buffer, we assume only slightly or almost no dissociations of weak acid. Since almost no dissociations of weak acid, that means that the molarity of the weak acid must be equal to the molarity given. And for this question, given 0.12 molar lactic acid, the weak acid, therefore the molarity of the weak acid, lactic acid, must equal to the molarity given, which is 0.12 molar. Step number 3, to find the molarity of conjugate base. Must remember, in buffer, we assume no dissociations of weak acid. Since there is no dissociations of weak acid, then it means that all the conjugate base ions must be from the basic salt dissociation. And the basic salt here is sodium lactate, and the sodium lactate will dissociate completely to give the cation and the anion. And the anion here is the conjugate base ions. From the balance dissociation equation, 1 mole of sodium lactate will produce 1 mole of the conjugate base ion. Hence, 0.1 molar of sodium lactate therefore will dissociate to give 0.1 molar conjugate base ion. And therefore, the concentrations of conjugate base ion is equal to 0.1 molar. In step number 4, we can then calculate the pH of the acidic buffer by substituting all the informations into the Henderson-Hasselbalch equation, and the pH of this acidic buffer is determined to be 3.77. Now we move on to look at case number 2, solutions mixing. For solutions mixing type of question, usually the volume and the molarity of the weak acid and also the volume and the molarity of the basic salt will be given respectively. And in the question also will be mentioned that in order to prepare the buffer solution, both solutions will be mixed or be added into one another. Step number 1, we can confirm that for this question, it is solutions mixing type of question. Must remember, for solutions mixing, dilutions occurs because the volume before mixing and after mixing in order to prepare the buffer change, and therefore the molarity of the weak acid and the basic salt will change as well. So in step number 2, in order to calculate the molarity of the weak acid, the dilutions formula M1V1 equals to M2V2 must be applied, with M1V1 refer to the molarity and the volume of the weak acid before mixing, and M2 and V2 refer to the molarity and the volume of weak acid after mixing. So after mixing, the total volume of the buffer is equals to 1 liter. Hence, V2 is equals to 1 liter. And with this, we can calculate that the M2 is equal to 0.1 molar, and therefore the molarity of the weak acid in the buffer solution is equal to 0.1 molar. In step number 3, we want to determine the molarity of the conjugate base. Remember, in the buffer, we assume that there is no dissociations of weak acid. Therefore, all the conjugate base must be coming from the salt dissociation. Hence, in step number 3, to determine the molarity of the conjugate base, we must first determine the molarity of the basic salt. During the buffer preparation, when the basic salt is being mixed with the weak acid solution, dilutions occur. Hence, in order to determine the molarity of the basic salt in the buffer solution, M1V1 equals to M2V2, dilutions formula must be applied, with M1V1 equals to the molarity and also the volume of the basic salt before mixing, and M2V2 refer to the molarity and also the volume after mixing. After mixing, the total volume of the buffer equals to 1 liter. Hence, V2 equals to 1 liter. With that, we then can determine M2, which is equal to the molarity of the basic salt in the buffer, which is equals to 0.12 molar. And from the dissociation equation, 1 mole of basic salt will produce 1 mole of the conjugate base. Hence, 0.12 molar of the basic salt will give 0.12 molar of the conjugate base. In step number 4, to calculate the pH, we just need to substitute all the information into the Henderson-Hasselbalch equation. With that, we then can calculate the pH of the acidic buffer, which is equal to 4.82. Case 3 involves solid solutions mixing. For this case, usually been given the mass of the basic salt and the volume and the molarity of weak acid. And in the questions also mentioned to prepare the buffer solution, the solid basic salt is being added into the weak acid solution. So from the questions, we know that this question is case 3, solid solutions mixing. After identify the case in step number 1, in step number 2, we need to list out the molarity of the weak acid. Must remember, in acidic buffer solution, we assume that almost no dissociations of weak acid. Since there is almost no dissociations of weak acid, therefore, the molarity of the weak acid HOCl is equal to the molarity given in the questions, which is equal to 6.5 times 10 to the power of negative 4 molar. In step number 3, we want to determine the molarity of the conjugate base. In acidic buffer, we assume that there is no dissociations of weak acid. Therefore, all the conjugate base ions are from the salt dissociation. Hence, if we want to find the molarity of the conjugate base, we must first find the molarity of the basic salt solution, NaOCl. In the question, we are only being given the NaOCl basic salt in terms of mass. Hence, to find the molarity of the basic salt solution, first we must convert the mass to number of moles. To calculate the number of moles of the basic soap NaOCl, the mass is divided with the molar mass, 74.5 gram per mole, to get the number of moles of the basic soap as 7.503 times 10 to the power of -4 mole. To find the molarity of the basic soap solution, NaOCl, the number of moles that we get is divided with the volume of the solutions, 1 liter. And the molarity of the basic soap solutions therefore is determined to be 7.503 times 10 to the power of -4 molar. 1 mole of the NaOCl basic soap dissociate will give 1 mole of conjugate base OCl minus. Hence, 7.503 times 10 to the power of -4 molar of basic soap NaOCl will give 7.503 times 10 to the power of -4 molar of conjugate base OCl minus. In step number 4, we can calculate the pH of the acidic buffer by substituting all the informations into the Henderson-Hasselbalch equation to give the pH of the acidic buffer solution as 4.56. For case number 3, solid solutions mixing, sometimes the questions can ask the other way around by giving you the pH of the acidic buffer solutions and ask about the mass of the basic soap needed to prepare the buffer solution. To tackle this question, again, in step number 1, we identify the case first. So, very obvious, this is solid solutions mixing case. And in step number 2, we still list out the molarity of the weak acid. Again, in acidic buffer, we assume that there is slightly or almost no dissociations of weak acid. Therefore, the molarity of the weak acid is equal to the molarity that is been given in the question. And in this case, the molarity of the weak acid HOCl is equal to 0.25 molar. Step number 3, we still find the molarity of the conjugate base. However, for this type of questions, since pH is being given, therefore you need to substitute the pH into the Henderson-Hasselbalch equation to get the molarity of the conjugate base. And for this question, the molarity of the conjugate base, OCl minus, is determined to be 0.2723 molar. After we get the molarity of the conjugate base, in step number 4, we can use the molarity of the conjugate base to determine the molarity of the basic soap. From the basic soap dissociations equation, 1 mole of the conjugate base is produced by 1 mole of basic soap. Hence, 0.2723 molar of conjugate base OCl minus is produced from 0.2723 molar of the basic soap NaOCl. After we get the molarity of the basic soap NaOCl, then we can calculate the number of moles of the basic soap by multiplying the molarity 0.2723 molar with 1 liter volume of solution to get the number of moles of basic soap NaOCl as 0.2723 mole. To determine the mass of the basic soap NaOCl, we just multiply the number of moles with the molar mass of NaOCl to get the mass of the basic soap NaOCl as 20.29 grams.